All right, V is equal to 250 pounds. So we've got a nice V going down here. Spacing between the nails is 1.25 inches. 1.25 inches. Determine the shearing stress in each nail and the main shearing stress in the max shearing stress in the beam. Okay, well, in each nail, they're glued, I don't know why I can't do this, but they're glued right here. So we need a cut right there, and that's gonna cut all the way down here, right? So what we really want to use is tau is equal to VQIT. Okay? And so how are we going to do this? Well, we need a couple things. They gave us V, so thank you for that. But now we need Q. Q is equal to the area times the distance of that centroid from the centroid axis. So this is symmetric, luckily. So the centroid is going to be right here. And so we just have to see this total distance is what? Let me see, this total distance is 3.5 and 3/4. So 4.25. 4.25 for this side. And then where is my A going to have its centroid? At 3/8. So this is 3/8. So my Y, my A is going to be 3/4 times 5. 3/4 times 5. My Y is going to be 4.25. 4.25 minus 3.3/8, right? Because we want to know the distance of the centroid of the portion of area that is creating the shear from the centroid of the overall cross section. So that takes care of this part. Let me see. 3/4 times 5 times 4.25 minus 3/8, which is going to be 14.5. And I know right away that this is incorrect. This is incorrect. And the reason for that is because 3.5, we need to do here, this is 3.5, hold on, 3.5 divided by 2 plus 3/4. So here we got something a little bit different. 3.5 divided by 2 plus 3/4 minus 3/8. So it's really 3/4. So you got to be careful with the dimensions. Multiply by 3.5 divided by 2 plus 3/4 minus 3/8, which is 7.969. So this is 7.969. What is it? This is in inches to the third, but it's not a volume. So now we have our Q here. What else do we need? Well, we need our I. So how are we going to find our I? Well, these are two shapes, a small square and a big square that are concentric on the centroid. So that's pretty nice because all we have to do is 1 over 12 times the big square, which is 5 times, I don't know if it's a square, it's probably not a square, 3.5 plus 3 halves, 2 times 3 over 4. And that is squared, not squared, to the third, plus minus 1 over 12 times the inner one, we're assuming it's a square, because they don't give us the dimensions of anything else. But 3.5 plus 1.5 is 5, right? So let me just do that. That makes it a little cleaner. 5 to the third minus 1 over 12 times, now it's not 5, is 3.5 times 3.5 to the third. So what is that going to be? Well, we can factor out the 1 over 12 multiplied by 5 to the fourth minus 5 to the fourth minus 3.5 to the fourth, which is 39.6. So 39.6 inches to the fourth. So now we have our I as well. Now our thickness T, that's going to be this and this together. So we're going to say 3 over 4 times 2, so 3 over 2. So our thickness is going to be 1.5 inches. Let me write that nicely. 1.5 inches. And now we know what our shear is because they told us. Our shear, V, is 250 pounds. Okay, and now we're going to put all of these together. But first, let's think conceptually what we're doing. We're finding the shear, the average shear, kind of right here. Right here. And why would that help me at all? Well, because I have nails at regular intervals. So if I know the shear along here, then all I have to do is I have to multiply the shear by the area to get the shearing stress in each nail. So the idea is that once you find your tau, you multiply by the area. But now there is one thing that to me is a little bit confusing, and I'll explain it to you in a second. So tau is going to be equal to 7.969 inches to the third, and then we're going to multiply everything by 250 pounds. We're going to divide everything by 39.6 inches to the fourth, and then we're going to multiply by 1.5 inches. And what do we have? Well, 7.969 times 250 divided by 39.6 times 1.5 is equal to 33.54. And what are the units? Pounds over inches squared. So P, S, I. Now, we need to multiply, so this is tau is equal to the shear that's happening along those arrows. Now, if I multiply the shear by the specific area, because we're saying that that shear happens everywhere. I think I'm up to something. We're saying that that shear, well, not here, sorry. It happens where there's wood. So here, where there's wood below. Oh my gosh. So where there's wood below, we got shear. So here, there's wood below, and here. And we're saying that this shear happens all around here. But if I multiply it by the area of a specific nail, like this, then what I'm gonna get is I'm gonna get the shear borne by that nail. So, I don't know if I use the right word, but let's keep going. So, the shear for each nail is gonna be equal to tau times the area for each nail, which is going to be equal to 33.54 pounds per inch squared, multiplied by, they said our spacing S is 1.25, and our width is 3/4, so 1.25 inches times 3/4, which is 0.75 inches. So 33.54 multiplied by 1.20 multiplied by 1.25 times 0.75 is equal to 31.44 pounds. And so that's the answer to our part A. What about part B? The max shearing stress. Well, the max shearing stress occurs at the neutral axis. So then we have to look at all of this. And I'm going to redraw it just so that we have a better visual that we can understand. So right here, then we have one right here and one right here. And I'm only going to draw above the neutral axis. So here, we're going to say this is my neutral axis, and we're going to have the dimension 3/4. So this is 3/4 inches, and then this is 5 inches, and then we have 3/5 over 2. So what do? We want to find the shear about this point. And so we know tau max is going to be equal to VQ over IT. Now V, they told us, is 250 pounds. So we have V. V is equal to 250. 250 pounds. Now let's work on our Q. Our Q now is going to be everything. So it's going to be everything above the neutral axis. So it's going to be this and this. But our Q is composed of two things. Our Q is composed of the area, which we can calculate, and the distance y. And what we can do is, and some people don't realize this, is that we can decompose them into single areas. So why don't we say that this is 1, this is 2, and this is 3? Because if we do that, then we're able to say that y1 is going to be at 3.5 over 4, from NA. So 3.5 over 4 from NA with an area, and we forgot one dimension, which is the 3/4, which is the same as this. So with an area of 3.5 over 2 times 3 over 4. The other one, the number 2, is going to look the same. So we're just going to multiply this by 2. And then we have the third shape, which is going to be the area, which is 3/4 times 5. And then we're going to multiply by its centroid, distance from the neutral axis, which is going to be 3 over 8 plus 3.5 over 2. And so now we should have our cube. So let's say 2 times 3.5 over 4 times 3.5 over 2 times 3 over 4. My calculator just decided it was not going to do all of that. So let me just say 2 times 3.5 over 4 times 3.5 over 2 times, and I don't think I should have a times here. I think I should have 3.5 over 4. No, I do. Times 3 over 4 plus 3 over 4 times 5 times 3 over 8 plus 3.5 over 2. What do we get? We get a 10.27. 10.2, my gosh, I can't believe I got it right. 10.27 inches to the third. And now, what about our I? Well, our I now is going to be the same as before. It's for the total cross section, so 39.6 inches to the fourth. 39.6 inches to the fourth. And then finally, what's our T? Well, our T is going to be this and this. So our T is equal to 3/2, which is equal to 1.5 inches. So now our tau max is going to be equal to 250 pounds times 10.27 inches to the third, but it's not a volume, divided by 39.6 inches to the fourth, and times 1.5 inches. So 250 times 10.27 divided by 39.6 times 1.5 is equal to 43.22 pounds PSI. That's the largest shear stress. And so that's the answer to the part B of the question. All right. I hope this was useful to start reviewing transverse or shear stress, and I will see you next time.